The test bed that I actually have here with me on the desk is basically HIL 402, our latest product in the 4 series family. So it's a real-time hardware-in-the-loop simulator of the latest generation. And on top of that, we also have an interface card. Here you can see the interface card that is directly plugged into our HIL 402 simulator, running actually Texas Instruments Delfino DSP controller. So that's our system, and the system that we'll be basically simulating consists of a small microgrid. You can see here this is a one-line. This is a one-line diagram. We have a point of common coupling where our small microgrid is connected, is grid tied with a protective relay device. Here we have a diesel genset model connected to the bus number 1. On top of that, we have actually three-phase PV inverter that is controlled by AIT controller. AIT is Austrian Institute of Technologies. This is our partner company, partner institute that we work closely with. They have developed their advanced DSP controller that is actually running on this Texas Instruments Delfino card, and they were kind enough to share this with us. On top of that, we'll also have a 3-phase battery storage inverter that is controlled with the controller inside the HIL simulation environment. And this is a very new, very interesting development in the latest our software release, where basically now you can model inside the real-time simulation not just the power stage, but you can also model equally well the signal processing and the control part. So basically your inverter can be controlled from the real-time simulation. So in a way we have a hybrid system. We have a controller in the loop, that's the Delfino, and we also have the controller inside the simulation, plus all the models of the genset, transmission lines, protective relays, and so on. So this is the setup that we'll be running here, and at this stage we can shift basically to our real-time simulation environment. So for you guys that are not familiar with our environment, so basically, it consists of 4 key blocks: schematic editor, control panel, script editor, and test suite. So we'll start with the schematic editor, which is a way how you are specifying the schematic that you're trying to simulate in real time. And this is the microgrid that we are simulating, the one that you just saw the one-line diagram of. So what is really interesting, so basically here you have a solar inverter. That's the one that is controlled by the AIT controller. And if you look inside, you're basically seeing a complete power stage with the filter embedded inside the inverter block, so you can clearly see like the multi-level schematic feature. The second inverter that I mentioned is a battery storage inverter. It's a standard 3-phase 2-level inverter with the filter and the measurement. But what is really interesting and exciting here is that we have the ability now to model the controls inside using our signal processing elements. So what we have here is a very simple current controller. So we are measuring phase currents IA, IB, IC, converting them into from ABC to DQ, closing the loops in D and Q channel, and feeding the reference signal directly here. You can see basically now our inverters can get the commands, the reference signal commands directly from the simulation, and this is the system that we are actually running here. On top of that, there is a reduced order model diesel genset and 2 transmission lines here with basically two transmission line here with 2 switches that are emulating line-to-line and phase-to-ground faults and point of common coupling here as well. After the compilation process, to speed things up, let's switch directly to the simulation control. This is basically the part where we can specify all our sources, photovoltaic panel curves, contactor settings. So you can see all the contactors here. These are the fault switches that are introducing the faults face to face. SGC contactor is the AIT solar inverter contactor that enables the unit to engage and disengage. And then grid selection. This is the one that allows us to basically switch from the grid tie from the grid tie to diesel genset to the islanded mode. And that's the standard setting. So we have set up all the feedback signals so that our controller actually can close the loops and be able to maintain active power and reactive power references. So to look at the custom UI, we have basically built a small custom UI here where you can actually now interact in real time in real time. You can interact with our simulation. So you can basically see now we are in steady state. Let's look at the waveforms here as well. So we are in steady state, point of common coupling here. We can see that the grid selection, we have selected the grid active. So the genset is actually now not engaged. So we are connected directly to the grid. We are maintaining frequency at 50 Hertz, and point of common coupling voltage here is on the order of 420 volts. Okay. Also, as I mentioned, we see here a three-phase inverter that is controlled by the AIT controller. It's a PV inverter with the PV panel, and you can see actually here the IV curve of the PV panel and controls maintaining the maximum power point tracking. In the interactive mode, as you can see, it's very easy to change the PV irradiation. So by changing the irradiation, you can emulate profiles, how the clouds are moving across your PV panels, and you can see as we are moving the illumination directly, the maximum power point tracking is picking up. So this is actually, so the solar inverter injected currents are shown here in the corner, the right hand corner. The other inverter that is controlled directly inside the simulation, this is this three-phase battery inverter, and the IA, IB, IC currents are shown here. We have the ability to interact directly and change the battery voltage. So you can see here we are injecting about 34 kilowatts directly into this bus, and being able to provide active power. So interesting things, couple of interesting cases how we can just show certain features and the real interactivity with this small microgrid simulation running on 402. Simple event when we are introducing the load. So for example, now the passive load is introduced directly to the battery. You can see here immediately that as we're introducing the load, the voltage, we have the immediate voltage drop, and frequency of course is stable because the frequency here, it's the frequency of the grid. But what is really interesting is like what's going to happen in the case when we switch now from grid tie to the islanded mode. Immediately as we're switching, we can see that the voltage drop is significant simply because there is a long line, and the long line actually provides a big voltage drop. But at that event, you saw that the solar inverter disconnected in this transient event, and now it's back up again in the process. Also, you can see that we had a transient frequency event. as we disconnected, the frequency went up, and now it's back to the standard 50 hertz. Now, if we, for example, change the load immediately, you can see another big event, big spike in the frequency. This is simply because the genset cannot regulate the frequency quickly enough. And now we see a solar PV inverter trying to connect back again to the grid. But every single time it tries to connect, because it's providing active power in the silent mode, the frequency drifts outside the limits and basically trips the inverter back. So this is an interesting, simple example of basically oscillatory behavior where the limits on the frequency regulation are kind of like forcing us in the shutdown mode on the PV injection, and then we are reconnecting back and trying. You can see these spikes every single time the solar inverter tries to connect. It's basically coming back and getting disconnected. Now, if we add a little bit of load in this process now, because there is more load and the load and generation is better matched, the frequency swings are a little bit more moderate, tamed, and we are actually able to quickly get the frequency of the microgrid and island mode in the proper regime. So there are a lot of things and a lot of scenarios that now we can try and optimize the control, both on the inverter that is controlled inside the real-time simulation, as well as the externally controlled inverter. But I think at this stage we will leave this for another webinar, another video, where you guys can maybe dive a little bit more into the details of modeling and control. But basically to summarize, we were able to see and run a complete simulation of a small microgrid with distributed energy resources, protective gear, and transmission lines on a very very compact but very powerful HIL 402 that, with its versatility and capability, can actually support all these features.